Strategy and Insider, exploring future trends and their impacts.
Konnichiwa, and welcome to a new episode of the Strategy and Insider podcast. I'm Thomas, a partner at Strategy and the host of this podcast. As you might have guessed from my greeting, we're recording in Tokyo today, which is obviously Japan's bustling capital. A series of workshops as well as an international conference has brought me to this vibrant city, and I'm thrilled that I can leverage this opportunity to discuss a truly visionary and thought-provoking topic while I'm here. I'm talking about brain-computer interfaces, shortly known as BCI, which is a field dedicated to translating thoughts into actions. It is an absolute privilege and honor to be joined by Professor Masayuki Hirata, who is a distinguished and renowned expert in neuroscience and neurotechnology. So thank you very much for taking the time with me today, Professor Hirata.
Thank you very much for your kind introduction. I'm very pleased to be here today.
Super. First of all, let's get to know you a bit. Professor Hirata is a specially appointed professor at Osaka University, where he leads the Department of Neurological Diagnosis and Restoration at the Graduate School of Medicine. He's also the founder of GMAT, an innovative company focused on wireless implantable brain-computer interface technologies that operates since 2020. His academic background comprises both the technical as well as the medical skills needed, having studied engineering at the University of Tokyo, as well as neurosurgery at the University of Osaka. Since 2000, he has been a board-certified neurosurgeon as well as a specialist and instructor in epilepsy and clinical neurophysiology. Back in 2016, he was named professor at Osaka University's Department of Neurosurgery. Next to that, Professor Hirata is an active member of various societal committees, for example, the president of the International Society for the Advancement of Clinical Magnetoencephalography. He was actually honored with several awards, such as the International Catalyst Award from the U.S. National Academy of Medicine back in 2020. While I could obviously continue to detail his impressive credentials, this brief introduction highlights the wealth of expertise and experience Professor Hirata brings to our conversation. This is why I'm truly honored to have you with me today, and many thanks for being my guest on this podcast.
Thank you very much for your kind introduction.
So, Professor Hirata, we're meeting in the city center of Tokyo, which is renowned as one of the most populous urban centers in the world, with the greater Tokyo area boasting over 41 million residents. When I landed here last night, the sheer dimension of this city was quite overwhelming to see from the plane. You traveled here today from Osaka, which is about half the size of Tokyo's enormous proportions and also has 2.7 million residents. How do you feel when you arrive here in Tokyo, and what do you prefer, the capital or Osaka?
Yeah, the difference in size is not so much different, just double. The size of Osaka City is the half of that of the Tokyo City, but the most biggest different point is the business. Actually, Tokyo is the center of the business, so many young talented people want to gather in Tokyo. So the startup company, most innovative startup company, easy to obtain such young talented people. That is the most biggest different point.
Mm-hmm. And a mega city like Tokyo has obviously a wide array of challenges to the infrastructure, including the healthcare system, with hospitals and clinics, doctors' offices, or simply ambulance routes. Yet Japan is remarkably efficient in providing reliable and functional health services. What is, from your perspective, the secret to making it work?
Yeah, that largely depends on the dedication of physicians and the medical staff. However, this led to excessively long working hours, so labor reforms were introduced last year. As a result, manpower shortage have become more visible, making it difficult to maintain this high-quality service in some areas, especially in countryside. In Tokyo, we are doctor 10 together. Yeah, as I mentioned, the impact is limited. But the doctor shortage in country areas are very severe. At the same time, simply increasing the workforce would expand the medical budget deficits. So it's a difficult balance now. Yeah.
And I was mentioning earlier, Professor Hirata, that you are a board-certified neurosurgeon and you have an academic background in both engineering and in medicine. So to me, this sounds like a perfect combination of skills for your work in developing brain-computer interface technologies and for founding your company GMED. However, it surely is no easy task to translate the thoughts in a human brain into physical action. Could you give our listeners, and also me obviously, an overview of how those BCI technology operates and what GMED specifically focuses on?
Okay. Brain-computer interface technology consists of mainly the three core technologies. One is the brain signal measurement, recording, and the other is the brain signal decoding. And lastly, the device control based on the decoded results. First, to transfer human thought into physical action, the control the device just by thinking, we must measure brain activity-related movement precisely and instantly. Next, we need to accurately interpret what those brain signals represent. This is the decoding process. Second steps. And finally, we use those decoded signals to control devices. Among these three, the most technical challenge is precise brain signal measurement. For implantable systems, extremely high reliability and safety are required, making it one of the most demanded types of medical device. But once realized, it's difficult to replicate, allowing sustainable business development. So, GMED has focused on developing implantable brain signal recording devices for accurate brain signal measurement.
And basically, GMED was established back in March 2020 as a spin-off from Osaka University. What led to your decision to start the company, and what have been some of the greatest challenges, but also milestones along the way until today with GMED?
Yeah, okay. I initially had no intention of starting a company myself. I hoped exciting medical device companies would commercialize this technology. But because the technology was so advanced and the business model was unclear, no company wanted to take it on. So I decided to do it myself. Our biggest challenge was the casing of the implantable device. While the internal electrical circuit was solved domestically only in Japan, but Japan had no manufacturing company producing implantable medical device casing. Yeah. It has included the various know-hows. So it is not so easy. Yeah. So we reached animal testing with some capable companies in domestic companies. But when it comes to human clinical models, they declined, saying that they couldn't handle human implant.
So the national Japanese-based firms could not handle it. Okay, interesting.
Yeah, for human application.
Yes.
Just animal applications, okay. But human application, no. Yeah. So because the Japanese companies are extremely risk adverse, which makes high-risk medical device production difficult. So we then approached several overseas companies, including Germany. Yeah, but they were very slow to act. Discussion, but no action. Finally, we turned to U.S. assembling company. They were much amazed by our device and offered to do it for very reasonable cost. Yeah, they said, "What an amazing device! it is the very first time we see this exciting device. So that experience showed me why US continue to lead globally. Yeah.
So the US actually picked it up and produced it then in a collaboration model with you. So the primary target of GMAT's technology is to enable communication for individuals who are unable to speak, move, or use other forms of physical expression due to impairments. What is the main use case of your technology, and how closely are you developing something market ready?
As you noted, our first goal is help patients with locked-in syndrome. They cannot do anything. Yeah, they cannot move at all. So such people include those with ALS, amyotrophic lateral sclerosis.
So AMS, right?
Yeah. So our goal is to help such patients to communicate. Yeah. So by enabling patients to operate communication devices using BCI technology, we can solve problems facing by those who's lost the ability to use them. So we plan to expand step by step, allowing users to control a variety of devices, such as not only the communication devices, but also the avatar, the humanoid robot. And the final ultimate goal is to enable disabled people move by their own.
So basically the technology then is for supporting patients with, for instance, AMS to speak again, but also at some point to move again as part of an avatar setup. Did I get that right?
Yeah.
Okay.
The most issue that such patient facing is that difficulty in communication. So the first issue to solve is solve the communication problem.
And how many patients have you treated already with this? And how many have you implanted such a device?
Yeah. We are now the final step of preparing for this upcoming clinical trial of the implant of this BCI device. So we are planning to start the clinical trial next year.
And it's a phase 1 clinical trial then, I assume, right?
Yeah.
How many patients do you plan to include? Is this known already?
We cannot say the accurate number of patients, but about 10 or so.
10 or so. Okay, good. But it gives an order of magnitude. I mean, beyond your main goal to enable communication, what are other potential applications do you foresee for BCI technologies as a whole? Probably not only from GMAT, but what could BCI technologies do?
Our strategy is step by step. And the final goal is to enable people with disability to regain control of their own body. Yeah, and eventually to extend use to elderly or disabled people with functional decline. So the controlling a humanoid or avatar is already possible at the research level. Yeah. And ethically, the most important things is to ensure safety and moral integrity, ethical integrity. Ultimately, systems should prevent harmful or malicious action, even if the user intended them. So also in communication, it is critical to ensure the private thoughts, things we think but don't wish to say, remain private. That is another important point.
And how does the Japanese population think about, because you mentioned it, the ethical boundaries, right? So you're implanting a brain chip into a human body. Obviously, data is flowing onto the chip. You are decoding the signals and put that into action in the end. So a lot of data is involved. How is the Japanese population open or not so open towards the usage of this?
Yeah. You mean that whether they want to use it or not?
Yes.
Yeah. Basically, our device needs a surgical strategy. Most of the people don't want to undergo surgery. So it depends on the balance of the merit and the demerit. Demerit is that you want to undergo surgery. The merit, the performance we can obtain. So if people understand that they can use it safely, and they understand that that is a very good tools to utilize, many people want to use that. But the present point, that is unclear. So many people don't want to use it. But patients are different.
Yeah.
Locked in people, they can do nothing. So if they inform the merit and demerit and such a disabled people, the merit is much larger than the demerit, most of the people want to decide to use that.
So basically, as long as it is safe and benefits are clear, those people that are disabled are open to using it, while the general public is more inclined to say, I don't want to have a surgery, I don't want to have a brain chip in my head, basically.
Yes. Right? And the performance increased as the technology had grown up, the more people want to use that. So this step is very slow, that gradually changed, that the people mind will gradually change.
So healthy aging is a rising topic in the developed world, especially also in Japan. The country has the world's most rapidly aging society, with nearly 30% of its population over 65 and more than 10% being even over 80 years old. So recently, GMAT's CEO, Jin Nakamura, shared insights on healthy aging through enhancing motor and communication capabilities for aging individuals at a conference here in Tokyo, actually. In what ways could BCI technologies be integrated into existing healthcare systems to support such aging population? And how could this influence the longevity trend we currently witness in many Western societies?
Yeah. In the future, elderly individuals with reduced physical ability could also benefit from BCI technology. Today's medicine already restores function in other organs, for example, intraocular lenses for cataracts or artificial joints for arthritis. So likewise, BCI technology could restore lost neural function in the elderly. So rather than aging, we need to see continued progress towards healthy longevity. Okay, so beyond medicine, residential, that living space, and the urban environments, we also evolve to be more age-friendly, integrating BCI technology into ideal, inclusive societies.
And probably also pivoting towards something that recently also happened in March 2025. GMAT received actually an Early Edge Award from Japan's Electronics and Information Technology Industry Association, which is the country's biggest industrial association. And the prize is awarded to companies with emerging tech expected to have a substantial future impact, despite currently probably limited market visibility. In this regard, GMAT is kind of an underdog, competing against much bigger and more established brands in the field, such as Neuralink from the US. How do you view the BCI ecosystem evolving? And do you plan to collaborate with other stakeholders?
Yeah, the ecosystem will likely evolve from simple EEG switches and keyboard operation to natural speech decoding, avatar control, and humanoid operation. In parallel, living spaces, urban environments will adapt their design accordingly. Our goal is to co-create inclusive ecosystem with smart homes and smart cities. Since BCI involves surgery, it won't progress as rapidly as some expect. But based on my 30 years as a neurosurgeon, I'm confident it will steadily expand and establish itself as a sustainable, groundbreaking medical technology. In 10 years or so, I expect GMAT to be widely recognized as a promising medical device company offering revolutionary care. Our strengths lie in the implantable brainwave measuring technology, the precise signal acquisition without noise interference. Unlike Neuralink's robot-inserted electrode, our approach simply place the electrode on the brain surface. This avoids brain injury, allows long-term stable performance, and requires shorter, simpler, and less costly surgery. Reducing the electrode spacing can even increase the resolution to the smallest function units of the brain. So our technology, I'm very confident to have a merit compared even with the Neuralink technology.
Okay. And the research that you have done up until here at the university, but also at GMAT, this was largely in animals for the time being. Can you probably explain a bit what type of experiments that you have been doing over the last years on this?
The implantable device, we cannot implant the human now. So we have to, before that, we have to do that, confirm the safety of the implantable device. So we are doing many animal experiments, implanting such medical devices, visual devices into animals, and confirming their safety and also its performance, basic performance. The performance of the decoding technology, the neural decoding technology, we performed many clinical research using the patient with intractable epilepsy. Because to confirm the epileptic focus of in such epilepsy patients, we frequently place the brain surface electrode to identify the epilepsy foci and the brain functions. So using such electrode implanted in patients, we performed many clinical research of BCI, mainly regarding the neural decoding. So that we have many experience regarding the neural decoding technology. But for the safety of the implantable device, we have to do using animals.
Sure.
Yeah.
And you are also a neurosurgeon, of course. So you could, in principle, also implant the brain chip device into a human brain.
Yeah.
Can you share a bit how is this done? And how do you open up the brain? And how do you connect such a chip into the brain? And how do you connect neurons?
We don't implant into the brain. Just place the electrode on the surface of the brain. So basic surgical strategy, cut the skin, open the skull bone, and cutting the dural membrane surrounding the brain itself. So after we opening the dural membrane, we can see the brain surface. So all we have to do is just place the electrode on the surface of the brain. And close.
And so you place it on top, and then how is kind of the signal then coming? Is it at the outer surface of the brain, and you kind of detect the signal from the outer surface of the brain because the electrode are kind of laying on the brain, and that signal is then strong enough to measure the signal and have that decoded?
Yeah, compared the wearable electrode placed on the skin surface, if we place the electrode on the brain surface directly, the amplitude that is the brain wave signal larger, much larger than the skin surface electrode. About 10 times as bigger as compared with that of skin surface electrode. And if we implant the electrode on the brain surface directly, the external noise is blocked by the skull bone. So this double merit, we can obtain the very accurate brain signals without external noises. And also compared the needle electrode, the robustness to the noises is far more robust than that of needle electrode. So the brain surface electrode we use is very, very robust and accurate.
And one of the wishes of humankind is obviously, or probably not the wishes of everybody, but there is a dream that after death, that your brain can also continue to live, that memories can continue to exist, right? So kind of a dream, not saying in the here and now, but probably years out. Do you see ever the chance of this being possible, or what is your expert judgment?
Externalized.
Kind of.
In the computer.
Yes. What's your expert perspective on that?
It's possible, but very difficult to realize that the brain signal is so tremendous that to regulate all brain signal is almost impossible at this stage. So it is possible, but it is almost impossible at present.
And if there would be quantum computing, so way more powerful compute power to be realized in 5-7 years from now, would this become more of a reality, or how do you judge this?
Yeah, such advanced technology make it more and more possible to realize, but still difficult, I think. Compared to very low power consuming brain, such a PC computing, it needs power, electricity. Yeah, it's not so cost effective, I think. Yeah, much different. Human brain, even an animal brain, so sophisticated. Yeah. It's the result of the 400 million years. Yeah, it's an amazing art.
You're absolutely right. And if we think of the human body, many organs are better understood meanwhile through research, right? But I have the sense around the brain not really being 100% by any means understood. To what extent do you think we understand our brain yet in percentage? Is it only 2%, 10%? Is it 80%? Or how much kind of knowledge about our brain do we have?
Oh, it's also very difficult question. I think that we know just a few percent.
A few percent, huh?
Yeah.
I would bet around 10% we understand probably.
Okay.
Yeah, okay. So another use case, obviously, we talked about that earlier, is that disabled people, the reason for disabling, let's put aside for a second, but people that cannot walk or cannot move their arms anymore. There is the use case of using kind of an avatar or an exoskeleton around that disabled person to move again. To what extent is that possible in parts already today? And when do you think such an avatar, such an exoskeleton can really make people move in daily life again? Is that out long years, or is that coming sooner? What's your perspective?
Yeah, I think that in the technological point, it can be realized soon.
Okay.
But medical application requires many issues to overcome. So the regulatory things that we can solve so many issues. So it takes times. Yeah. But technologically, we can realize presently. Yeah. And also that my final ultimate goal is to move their own body using implantable functional electrical stimulation. For example, only if we place the electrode to the 5 nerves under the armpit, median nerve, radial nerve, ulnar nerve, musculocutaneous nerve, axillary nerve, these just placing 5 nerves for these 5 electrodes for these 5 nerves, we can control the whole upper limbs. Also, we place just placing the 4 electrodes for the called equine portion, we can control the gating function.
And that means if I come back to that arm, if you have the 5 nerves that you just mentioned, and then they get kind of triggered externally through electrodes, right? How are they going to be triggered then? Is this an electronic signal that is transmitted from human brain onto those nerves, or is that from external?
Yeah. Based on the BCI devices, the BCI device, how to stimulate this electrode based on the decoding result of brain activity. So if they just think, they can move as they want, even in the disabled people again.
So meaning that if you have that implantable device kind of layering on top of the human brain, non-invasive, into the brain, but layering on top, you are measuring signals from the brain through the BCI device. You're decoding this. And if that person thinks, I want to move my arm, you measure that signal that is transmitted to the electrodes to, let's say, the left arm, to those 5 nerves. And that is then triggering that the arm can actually move. Yeah, kind of. This is the connection from the brain to the BCI, decoding and sending signal to the nerves, to the arm, and then the movement happens.
Yes.
And this is going to be possible soon, you said, right?
Technology is possible, but we are doing now doing animal experiments. So gathering the many findings using the animals, now we can apply it to human application.
And the biggest barrier to using this in humans is then the safety around it.
Yeah, so many issues to use such technology presently. Because of the long-term stability of the electrode, or the long-term stability and the safety, and also the performance of such a technology. I only mentioned about the concept of my concept.
Yeah.
Just the concept.
Sure.
Yeah. And we are doing the animal experiments, so many animal experiments, but we are facing so many issues to overcome.
So let's probably take a step forward. 10 years from now, we would meet again, be it in Tokyo or Osaka, in GMAT's then flourished company side. What are the key things that we will have achieved until then when it comes to BCI technologies? What is it that you look back and would be proud to be part of such development?
Yeah, basically we are proud of BCI technology. But the related technology, as also we are very proud of it. Yeah, indeed, 10 years that several companies are doing a clinical trial. Yeah, the BCI technology that they approved for as a medical device to restore motor and communication function. So 10 years, that's just the first step. So 10 years, 20 years, 30 years, 40 years, gradually this innovative technology changed the world. Yeah, I think.
So basically, it takes quite some time still to make it to into humans fully. What can unlock a lot is new compute power through quantum computing. I understood. I also understood that you can measure brain signals, decode and send directly in a targeted manner signals to individual nerves to make the respective organs and parts of the body move. So really fascinating science, really fascinating concept behind, but also real life advancements that you're doing in your own company called GMAT, right? So really my sincere thanks to you, Professor Hirata, for sharing your profound expertise in BCI technology and for really enlightening us on this complex yet incredibly exciting topic. And to be honest, I will definitely take a lot away from this conversation today. And I wish you personally, obviously, the very best for your endeavors in academic research, but also at GMAT, and can't wait to see how your company will develop, and hope to meet again in a few years and have the chance to revisit the predictions from today.
Yeah. Thank you very much, Dr. Thomas, for this very exciting discussion. Thank you very much.
So, to all our listeners, thank you for your continued support. I hope you enjoyed the conversation as much as I did. Please share your thoughts with us on the various podcast platforms or shoot me a message on LinkedIn. We really appreciate all the feedback we receive and welcome your input to bring you more thought-provoking episodes in the future to come. But until then, sayonara and goodbye.
Strategy made real.